and welcome to our first video lesson in our sound and light unit. Today's lesson is going to be dealing with wave properties, and what we're going to be doing is looking at what is the difference between a mechanical and an electromagnetic wave. We're also going to talk about two different types of waves. One is called a longitudinal wave, and we're going to learn about the different parts within a longitudinal wave. The other wave is a transverse wave, and we also are going to learn about the different parts of a transverse wave. And then finally, we're going to discuss how waves actually propagate or move through space. So it's quite an exciting day. Let's get right to the discussion. So an electromagnetic wave versus a mechanical wave, what really is the difference? Really what we look for is how waves move through a medium, which is basically the material through which they travel. An electromagnetic wave is able to move through a vacuum, which a vacuum is basically just an area of space that's void of any type of particles. There's no atoms within that area. So an electromagnetic wave, an example of that would be something like light. Right? So light is an example of an electromagnetic wave. A mechanical wave is not able to transfer its energy through a vacuum. It must have something called a medium. And so what that means is basically it needs to have some vehicle or material through which to travel through. So right now you can hear my voice. Sound is an example of a mechanical wave. If we were in the vacuum of outer space and I started talking to you, it would sound like this. And so that is really the big difference between a mechanical wave and an electromagnetic wave. An electromagnetic wave can travel through a vacuum. A mechanical wave cannot. When a wave moves through a medium, it transfers only the energy, not the actual medium through which it travels through. So here we have an example of two different pictures. Basically what the point of these is that you'll notice the dots. If you follow this red dot right here that I've highlighted yellow, you'll notice it just moves back and forth. The dot itself is not actually traveling across the screen. And so this would be an example of, say, like a water wave or something of that sort, where actually the medium is not moving or being transferred, it's just the energy. You'll notice, like, and if you go to a lake or an ocean, it's not like all the water piles up on the shore because the waves are traveling through it. Instead, it's just the energy that's actually traveling through the water, not the actual medium itself. There's two different ways that we can kind of describe a wave. One is called a pulse, and a pulse is just one single disturbance, which you can see in this image here. It's just one push of energy through whatever medium it's traveling through. A periodic wave is what we call wave train, where it's continually happening over and over again. It's repeating itself. So there are two types of waves that we mentioned earlier. The first is a longitudinal wave, and a longitudinal wave vibrates parallel to the direction that it actually moves. So that sounds really complex, but basically if you look at this image, you'll notice that the particles within this diagram are vibrating back and forth, such as drawn by this arrow. You also will notice that the direction that the energy is moving is parallel to those vibrations. The fancy name for that is propagation. Propagation is the movement of the wave. So it's kind of like if you've ever watched a worm move across the ground, it expands and contracts in the same direction that it's moving. An example of this type of wave would be sound. Sound is a longitudinal wave. If we take a look at like the anatomy of a longitudinal wave, there's some parts that are important for us to note. The first is when the wave gets kind of smushed up, the medium through which it's traveling gets smushed together, that's called a compression. The compression in this diagram can be seen right here, where the particles of this wave are getting kind of smushed together, clumped up. The parts where they are stretched out or expanded, that's called a rarefaction, which would be this part of the wave right here. The distance between compression to compression or rarefaction to rarefaction is something called a wavelength. So that is the distance between those 2 points. A transverse wave is a wave where the particles vibrate, or the medium vibrates perpendicular to the direction of travel or propagation. And so if we take a look at this diagram right here, you'll notice the particles are actually moving up and down. They are vibrating up and down. But the energy from the wave is actually traveling this direction. It's moving that direction. So my black arrows are drawn vertically, my magenta colored arrow is drawn horizontally, and this makes a 90-degree angle between one another, which is the definition of perpendicular. You have the vibrations moving perpendicular to the direction of propagation, and that by definition is what a transverse wave is. An example of a transverse wave would be something like light. If we take a look at the anatomy of a transverse wave, we have some common terms, one being wavelength, but there are different parts to a transverse wave because you have that up and down motion going on. And generally speaking, in this course, we talk more about transverse waves than we do longitudinal waves. So let's really dive into this. The tops of, or the peaks of the wave are called something called a crest. A crest is where the wave tops out. The bottom of a wave is called a trough. If any of you have ever watched like pigs eat at a farm, they usually put the food in a trough, and that's kind of how I remember that this would be the low point where I'd stick the food for a pig. A crest, if you've ever climbed a small hill or something like that and you reach the top, you may say, I've reached the crest of the hill. This would be the peak of the hill. The amplitude is the maximum distance from equilibrium. And equilibrium would be like if the wave wasn't moving at all, it'd just be at its what's called rest position. And that's represented by this black bold line here that says rest position. So the amplitude is actually the distance from that rest position to either the crest or from the rest position to the trough. Either one, same thing. The amplitude would be the same in either case, but that's represented by the capital letter A. A wavelength is the distance from either crest to crest or trough to trough. It doesn't really matter, or any other part that is kind of the same point on the wave. So a wavelength could also be from here, from this point to this point. Basically, in my definition here, it's the distance for one complete vibration to have occurred. So this wave would have gone through one whole cycle to get to that point again. Stay tuned for our next video, which will be about the wave equation. See you later.